back to the tetrahedron chemistry classes. So in today's class I am going to discuss a very important concept of the stereoselectivity, right? And in the stereoselectivity also today we will see the diastereoselectivity, right? In the later classes I will also discuss the enantioselectivity, but in today's class I will discuss the diastereoselectivity, concept of the diastereoselectivity, especially for the carbonyl compounds, right? You know this carbonyl compounds, whether they are the aldehydes or the ketones, they have the tendency to undergo the nucleophilic addition reaction, right? So I hope this much of basic organic chemistry you all know. So, but for the beginners, if for the beginners you can understand in that manner. For example, if I am having this carbonyl compound, right? Here you can see this CH3 is here and this hydrogen is here. So this is your acetaldehyde molecule, and you know this oxygen is electronegative in nature, so it will get a negative charge over there, right? And this carbon is positively charged, okay? And you know positively charged carbon is basically electrophilic in nature. So this carbon is electrophilic, electron loving species in the aldehyde or in the ketone, right? So when it is electrophilic in nature, it always seeks your nucleophile, right? So any nucleophile can add to this carbon, and that carbonyl group will convert into some other functional group like alcohol, right? So in short, what you should note that due to the presence of this oxygen, electronegative oxygen, this carbon is electrophilic in nature. So that's why it has a natural tendency for the nucleophile, and it is the unsaturated compound. So any nucleophile can add to this particular carbon to give the saturated compound, right? So this is just the basics of the organic chemistry. Okay, I hope this is quite clear to you. So whenever you do this nucleophilic addition reaction to the carbonyl compounds, right, then there is an instance when the concept of the diastereoselectivity applies. So when the concept of the diastereoselectivity will apply, for this you need to understand that particular reaction. So for example, I am writing this particular reaction here. Say this is your phenyl, okay, and this phenyl is connected with the methyl over there and hydrogen here, and this is your carbon double bond oxygen, right? And this is your CH3. So this is your carbonyl compound, right? This is your ketone, substituted ketone. This is the carbonyl group, this is the methyl group, and this is another alkyl group which is the quite bulky in nature. But if you clearly focus on this particular carbon atom, I am putting the asterisk or the star on this particular carbon atom to explain you that this carbon is chiral in nature, right? That means stereochemistry is involved here, and it is very easy to identify the chiral carbon when your carbon is attached with the 4 different kinds of the group. Then it is asymmetric carbon. So here this phenyl is there, benzene is there, and here methyl is there, and hydrogen is here, and this is the rest of the group. So this is basically your carbonyl carbon, your chiral carbon just next to the carbonyl carbon. So this is your carbonyl carbon, and just in the vicinity of this carbonyl carbon you are having this chiral center. Now if you do the nucleophilic addition reaction onto this particular system, and nucleophilic addition reaction, what you can do, say you can take the sodium borohydride, right? You can take the sodium borohydride, NaBH4. This is the step number 1, and after that you will do the protonation of this. So protic workup, I am writing protic workup, that means reaction with the dilute acid. So what will happen in that case? You will get this particular product, PH, carbon with CH3 over here, and hydrogen is here, and this oxygen will convert into the alcohol, and one of the hydrogen will come here, and this is the CH3. So this molecule was already having one chiral center here, and you have produced the new chiral center in the molecule as well. So 2 chiral centers are there. So this is known as the asymmetric induction. This is called the asymmetric induction because you have introduced a new chiral center. So when this happens basically, So not only the single products form, more than one products are formed, and those products are the diastereomers of each other. That's why the reaction is called the diastereoselectivity. If you don't know what is the stereoselectivity of the reaction, so you can go through, you can check in the description box. I'm giving you the link of the stereoselectivity where you can understand the stereoselectivity in a very simple and a lucid manner. But right now you can understand in that manner. Stereoselective reactions are those reactions in which more than one products are formed, and all the out of the product formed, one is the major and others are minor, and all these products are the stereoisomers of each other. Then such reactions are called the stereoselective reactions. And exactly the same thing is happening here. I have produced a new chiral center here, okay, and along with this particular compound I'll also have the another compound, and that particular compound, when you relate with this one, you will find that there is a diastereomeric relation between the two. But I am not right now I am not writing the another isomer here, but you can remember in that manner we have shown only one particular isomer here. Another isomer will also be there, and these two isomers would be the diastereomers, right? And one would be major, other one would be the minor one. That's why the reaction is called the diastereoselective reactions. That's why this heading is here, diastereoselectivity of the nucleophilic addition reaction of carbonyl compounds. And here I have written the asymmetric induction. So what is the meaning of the asymmetric induction? When a new chiral center is created in a molecule which already contains one or more, right? So like this, in this particular example, this is already having one chiral center, but it may also have the more than one chiral center, but in this example only one chiral center is here, right? And we are creating the new chiral center here. Then diastereomers are formed in the unequal amount. The reaction is said to be the diastereoselective reaction. And to know the major and the minor product in that in this reaction, which isomer would be the major one, which isomer would be the minor one, few empirical rules like Cram'S rule, Falcon and model, Prelog's rule, and Horio's methods are there. So by using any of these methods, whether it is the Cram'S rule, Falcon and model, Prelog's rule, or the Horio's method, you can predict the stereoselectivity, right? Or the diastereoselectivity, and then you can find which compound would be the major one and which compound would be the minor one. I hope this is quite clear to you. So now moving further, say next is, see, in this particular class I will only discuss the Cram'S rule. Okay, I will discuss this Cram'S rule in the pretty much detail, and in the subsequent classes I'll also explain the Falcon and model, Prelog's law, and the Horio's methods. Okay, so first of all you should know how to draw the projections, Newman projections of these carbonyl compounds. It is very, very important. So I'm just giving you the example how we can draw. Say you have been given this particular, say this compound is given here. Okay, so how I can draw the Newman projection for this one? Say this is the oxygen and here one carbon is there, right? And this is the CH3. So this is your carbonyl group. This part in the center, this carbon is here, and this is the oxygen, and this CH3 is attached here. Okay, so this is how we can write. And see, and you are looking this molecule from this particular direction, right? Your eye is somewhere here. So you are looking the molecule in that manner. So this is actually your front carbon, and the back carbon is the rear one, or rear carbon, or the back carbon. Okay, so this is where basically carbon double bond oxygen and the CH3, and you know in the Newman projection formula the rear carbon or the back carbon is shown by the circle. So this particular circle basically is representing this chiral carbon. Okay, and this chiral carbon is having these three groups, PH, CH3 and H. So you can put all these groups here just like that. Say this is your pH, which is a phenyl one, okay, and then you are having hydrogen, and then you are having CH3. So this is how we can draw the Newman projection formula for the carbonyl compound. So if you are not aware about the Newman projection formula, Sohor's formula, Fisher formula, so again you can go again you can check the description box where I'll give you the link of these projections as well, how to convert Newman into the Sohor's, Sohor's into the Newman, and Newman into the Fisher, and Fisher into the Sohor's. Everything is given in that particular lecture, and you can find the link in the description box. I hope this much thing is quite clear to you, right? So right now, if you are not very comfortable in understanding the conformations of your carbonyl compound, so you can only learn the things which I am teaching here, okay? In the separate class, I will also explain the your conformations of the carbonyl compounds as well, okay? So now we will discuss the Cram'S rule. So here you can see what is the Cram'S rule. So Cram'S rule states that when a nucleophile attacks a carbonyl carbon, the resulting product will have the nucleophile positioned on the side of the carbonyl group with the smallest substituent. So this is the statement which you can find in the stereochemistry by D. Nasipuri. There is a very, very famous book of the stereochemistry. After Eliel, that D. Nasipuri book is the most famous book of the stereochemistry, and this statement I have taken from there only. Right now you can understand, you can learn only this statement, and then I'll apply this statement to the molecule as well, okay? And there are various kinds of the Cram'S rules modifications are there depending upon the type of the substrate, okay? And first very simple one is the Cram'S open chain model. So what is the Cram'S open chain model? I am going to explain, and then I'll apply the statement which actually is given in the D. Nasipuri book. So for example, I am drawing this configuration of the carbonyl compound. Say this is your oxygen, okay, and here one alkyl group is attached, right? And then you are having the rear carbon over it, and in the rear carbon you are having one alkyl group, and it is the smaller one, say it is the methyl, right? And then you are having another alkyl group, and I am marking this alkyl group as M. That means M stands for the medium, say it is ethyl group, okay? And then I have attached one more group which is your RL, where L stands for the large, say it is your propyl group, okay? So this is methyl, this is ethyl, this is propyl. That means rear carbon is the asymmetric carbon, okay? Rear carbon is the asymmetric carbon. And to make you understand a little bit more clearly, I can draw this structure here again. Say this is your carbon double bond oxygen, this is your R, right? And here another carbon is there, and then you are having three groups, RS, RM, RL, okay? And you are viewing this particular molecule from this particular direction. So this is your front carbon, and this is the oxygen connected with it, and this is the R here. That carbon is the rear carbon which I have shown with the circle, and then this is your RS, then this is your RM, and this is your RL. So this is the Newman projection formula for this particular compound. I hope this is quite clear to you, right? Now what we can do, see, if I go back, please remember this particular reaction, right? Here I'll react this carbonyl group with the your nucleophile. See, your nucleophile may come from your say organometallic compound, or from the hydrides. So this is a metal hydride basically. So two kinds of the reagents basically can produce your nucleophile in this particular reaction. Either you can use the metal hydrides, okay, which I have used here. Or you can take any organometallic compounds like Grignard reagent as well, okay, organometallic compound. So this organometallic compound and this metal hydride basically will give you the nucleophile. This is very, very important. And in the second step, you will do the protic workup and your end product would be the alcohol. So you please keep in mind the end product would be the alcohol whenever we do these kinds of the reaction. This is very helpful, okay. Now what we can do here, say for example, I am taking any metal hydride from here. Say this is my metal and it is connected with the alkyl group. So this is alkyl metal, right? Not this is not metal hydride basically, but it is a kind of the organometallic compound. Right? And you know, metal is basically less electronegative than your carbon. So this will get a positive charge over there. And your R is the negatively charged. That means this R part is your nucleophile. It is your nucleophile. Okay. So what will happen? You know, your metal is positively charged and in the carbonyl group your oxygen is negatively charged, which I already told you. You can put your small negative charge onto this particular oxygen atom and that carbon is the positively charged carbon. This is for understanding. So what will happen in that case? The interaction will take place between the electronegative oxygen and your metal and the coordination will occur from here, right? And now you can see here this R group can add to this nucleophilic carbon, right? This carbon is electrophilic carbon, not nucleophilic carbon. It is electrophilic carbon. When it is electrophilic, only then the nucleophile can attack on it. Now this nucleophile have the two different pathways to approach onto this particular carbon atom. First pathway is this one. It is coming here. This R is adding to this carbon and it is approaching from this particular direction. When it is approaching from this particular direction, what will happen? You see. And after, you will also do the protic workup here, right? Protic workup. That means your end product would be the alcohol. If I go back, you know, this oxygen will convert into the alcohol. Please remember, this oxygen will convert into the alcohol. So now, what product you will get here in that case? Say, you know, this would become OH. Okay, this would become alcohol. So what I can do, I can write my alcohol in that manner. So this is my OH, right? It has converted into the alcohol and this carbon is here. And just in the bottom of this particular carbon, your alkyl group is here. So what I can do, I can write this alkyl group here. Okay. And you have already seen that this alkyl group is coming to add onto this particular electrophilic carbon. So this is having R dash here. This is your R dash. Okay. And in the rear position, you are having this rear carbon, which is basically this one. And that rear carbon is having 3 different groups. Just like that, you see. This was your RL. That means the larger group. So I can write RL here. And then you can see here, this is your RS. Okay. So I can write RS here. And then your RN. This is your RN. Right. So this is the complete staggered form. Most stable form. This is the complete staggered form. And in that case, you can see here, this R which is coming from the organometallic reagent is actually in between the smaller alkyl group and in between the medium alkyl group, right? This is the very important concept. So this will give you the one kind of the isomer. This will give you the one kind of the isomer. Okay. So now what can happen? See, first of all, you should remember this thing. This carbon is here and this oxygen has converted into the alcohol. This R is coming here. So this R is here and this is the bottom alkyl group and this is the rear carbon, and that rear carbon is having the Rm, which is here. Okay. And this is the Rl and this is Rs. This is a complete staggered form of this one. This is one of the isomer, right? And that isomer is basically the major isomer. So I am writing it as major isomer. Okay. And also remember, in this major isomer, this carbon actually is the chiral carbon, and the newly produced carbon, which is this one, OH is here, R dash is here, R is here, and the rear group. This is also the chiral carbon. Two chiral carbons are there. That means it is a certain kind of the stereochemistry is involved in this particular molecule. Now what can happen in the second instance? See, protic workup I am writing here. Protic workup. And now in the second instant, your R, this R is actually coming from this particular position, from the side of the medium group. Okay, from the side of the medium group. So your next isomer will be formed. So how the next isomer will be formed? Please see, your R is coming from here. That means that part will have the R dash. This R dash coming from here to add on to this electrophilic carbon. That means that part is have your R dash. So I am writing R dash here, and this oxygen will convert into the alcohol. So I am writing OH here, and in the bottom you are having R. I hope this is quite clear to you. See, when your R is adding here, so this oxygen will be pushed to this particular direction. So alcohol would lie somewhere here, and this is your R group. Okay. And this is the rear carbon, and of course your rear carbon will have the again different types of the groups attached to it. This is your larger group. Okay, this is your medium group, and this is your smaller group. So Cram'S said that whenever your alkyl group or your hydride approaches to this nucleophilic this electrophilic carbon, it has to go through the side of the smaller group to avoid the repulsion or the steric hindrance, right? However, the second pathway is also available. So your next isomer will also be formed, which is against the Cram'S rule. So this would be the minor one. Okay, and say this is your A, this is your B, and when you relate this A to B, then you find these two are diastereomers of each other. Diastereomers of each other. You know, diastereomers are those stereoisomers which differs in the configuration at least at one carbon atom. Okay, we will see the real example of this as well, right? This is the generalized example, right? This is something very important you need to understand. And see, in the Nasipuri you can read that particular statement why actually this R is preferably adding to this electrophilic carbon from the side of the smaller group, right? So it is reasoned that the carbonyl being complex with the metal, okay, this particular reagent becomes the bulkiest group, and thus it is better placed between the medium and the smaller group. Say this is a smaller group, this is the medium group, and this due to this coordination becomes very bulky. So to avoid the steric repulsion, it is better placed in between the medium and the your smaller group. That's why it has to attach from the side of the smaller group. Okay, this is something very important. You can find that particular statement in the Nasipuri book. Okay, this is just the one example. Now what I can do, I can give you the real example as well. Please focus here. Open chain model, Cram'S open chain model. So here you see, this is your phenyl, okay, and that phenyl is connected with the carbon. CH3 is over there, and here is hydrogen, and this is your carbonyl group, and this is your CH3, and I am converting it into the your Newman projection formula. So this is your CH3, okay, this is the carbonyl part, and this is the rear carbon, okay, and this rear carbon is having what? See, this rear carbon, this is the rear carbon which is having hydrogen, CH3 and the phenyl. So I am writing the hydrogen, CH3 and the phenyl. So this is my PH phenyl, okay, and this is my hydrogen, and this is my CH3, right? Now you can see here, this hydrogen is the very smallest one, so I am writing S here, and this is the medium group, methyl, and this phenyl is the larger group, okay. So whatever the alkyl part or the hydride part will add to onto this particular carbon atom, this has to come to this particular direction, right? This is something very, very important you need to understand, okay. Now what I am doing this reaction in the two different manners. Say for example, I have reacted this with the lithium aluminium hydride, okay. I am taking LAH. LAH is the lithium aluminium hydride. So here I am writing aluminium, and then you see hydrogens. LiAlH4 is the formula, and of course your lithium would also be there, okay. Now what will happen in that case? Your aluminium will coordinate to this one, right? This will become the bulkiest one, so it is better placed between the smaller and the medium group, okay. Now one of the hydrogen from this aluminium hydride part has to add on to this particular one, and after protic workup this will convert into the alcohol, please remember, okay. I am not writing that particular protic. See, for this I am writing the protic workup here, protic workup. So after protic workup this will become alcohol, right? So what product actually I will have in that case? So here my hydrogen is coming to this particular direction. So that part is having, see, this part is having the hydrogen, okay, and this O will become the alcohol. So you are having this kind of the conformal. So this is your OH, and this is the hydrogen which is coming from the aluminium hydride, okay, and in the bottom you are having the CH3, and this is your this is your rear carbon. I am taking the different color for this rear carbon, okay, and then you are having the completely staggered form, and here you can see CH3 is here, and hydrogen is here, and this is your pH, okay. So this actually product which I have formed here, this is the major product in that case. Somewhere 70% yield is there. It is mentioned in the Nasipuri as well, 70%, right? So this is known as the trio. This compound is the trio compound, okay. So what are the trios? Trio and erythro nomenclature. In the trio nomenclature, two similar groups are placed on the same side of the Fisher projection formula. So when you draw the Fisher projection formula of this one, then you will find the two same groups will be present on the same side. So if you know how to convert this into the Fisher projection formula, then it would be very, very easy to for you to understand the concept of the diastereoselectivity. But if you don't know how to convert this into the Fisher projection formula, then you can go through my earlier lecture, for which I am giving you the link in the description box. But for the beginners, I am also explaining this thing here. So now I am converting this into what? Fisher projection formula. So for Fisher projection formula, I need to convert this molecule into the Sohor's formula first. So this is your front carbon. Please remember, this is your front carbon, this center one, and this front carbon is having OH, H and CH3. Say I am writing in that manner. Say this is my OH and this is my H and this is my CH3. Okay, and I am looking my molecule from this particular direction. So this is my front carbon. Okay, so on the back of the front carbon you will also have your rear carbon. Rear carbon is this one, this circle. Okay, so this is your rear carbon, and my rear carbon is having methyl over there, CH3. You can see this CH3 rear carbon I am putting here, and the hydrogen is here. So I am putting my hydrogen is here. Okay, and then you can see this pH is also here. So I am adding this pH here. So this is the Sohor's formula. This is what? Sohor's projection formula, and this was your Newman projection formula. Okay, now I need to convert this into the Fisher projection formula. So to convert this Fisher projection formula, it is mandatory to rotate this bond by 180 degree. Okay, so I am writing here 180 degree rotation. See, it will not change the configuration. If I rotate this molecule by 180 degree centigrade, it will not change the configuration. So it is allowed to rotate this particular bond by 180 degree centigrade. So when I rotate this by 180 degree centigrade, so this CH3 will come down because this line will make 180 degree angle. So this will come down and that hydrogen will come here and that pH will go there. Okay, after 180 degree rotation. So after 180 degree rotation, the front carbon will not change because I have fixed the position of the front carbon. Okay, that means I was holding this particular carbon and rotating this particular bond. Okay, and when I go there, then after 180 degree centigrade, this 180 degree rotation, this CH3 will come down. See, if I rotate this bond like that 180 degree, okay, so this will come down. So it is coming down, and here this will go up. So now my hydrogen is here and my CH3, my pH is here. So this is the rotated form. Now I can convert this into the Fisher projection formula. Say this is my carbon number 1, this is carbon number 2, this is carbon number 3, this is carbon number 4. So what I can do, I can simply write my 4 carbons. Okay, like that. Okay, I am giving the number to this one again. So this is 1, this is 2, this is 3, and this is 4. Okay, my carbon number 1 is the CH3. You see here, and carbon number 4 is also the CH3. So I am writing CH3 here. Right? And then you can see here, my carbon number 2 is having H on the right hand side. So I am putting my OH here, my H here. And the left hand side of carbon 2 is having the OH, so I am putting my OH here. Okay, now in the rear carbon you can see on the right hand side you are having the pH, so I am writing pH here. Okay, and on the left hand side I am having my hydrogen, so I am writing my hydrogen here. Okay, so this is basically the trio one. Trio, that means the two similar groups will be on the opposite side of the Fisher projection formula. So these two hydrogens are similar and they are on the opposite side in the Fisher projection formula. So this is the trio compound. This is the trio nomenclature, right? And if you want to give the configuration to each center, then you can write the configuration as well. So I am telling you my carbon, see how many chiral centers are there. So to know the chiral centers, I need to remove this numbering. Right, okay. This carbon is the chiral carbon, and this carbon is also the chiral carbon. Please remember, these two carbons are chiral. How? It is connected with the 4 different groups: 1 hydrogen, 1 methyl, 1 pH, and the rest of the group. This is also the chiral carbon because it is connected with the 4 different kinds of the group: 1 methyl, hydrogen, and then your OH and the rest of the group. That means 2 chiral centers are there. And if you assign the configuration of these chiral centers, then you will find this chiral carbon is basically having the configuration of R, and that particular carbon is having the configuration of S, right? I hope you are aware how how to give the absolute nomenclature or absolute configuration to the chiral carbons. That means the RS system of nomenclature, rectus and sinister. If you don't know how to give the configuration to these particular chiral carbons, again I am giving you the link in the description box. You can go through the description box and learn from there actually how we can convert. But believe me, this is your R, this is your S. I am not actually telling you how to convert, how to give R and S configuration to this one. This is up to you. But if you don't find these things quite easy to understand, then you can always comment in the comment section, and I'll give you the details as well. I hope this is quite clear to you. Now in the second step, what we can do here, you see, one of my hydrogen, now I am following the different path. Say it is coming from this particular direction, side of the medium group. It is approaching, this hydrogen is approaching onto this carbon through the side of the medium group, right? So this means now this part will have the hydrogen here and alcohol will go here. So I will draw this thing again. Protic workup I am writing. Protic workup I am writing. Okay. And then you see I am having this feature. Your alcohol will be here. Your hydrogen will be here. This is your CH3. I hope this is quite clear to you. Hydrogen is coming from this particular direction, so this hydrogen will be here connected with this electrophilic carbon, like that only. This will convert into the alcohol and it will be pushed here. So this is your OH and this is your CH3. Okay. And then you are having the rear carbon, the back carbon. Okay. And in this back carbon, you are having this configuration here. Okay. So this is your pH. I am writing pH here. Please remember. Okay. And then you are having my CH3 here and then my hydrogen here. In the Newman projection, you can see here these two are on the opposite side. Okay. But you see here in that case, on the opposite side. Here if you convert this into the, see, this is at the 180, see this angle is actually the 180 degree angle. So that means they are actually they will fall onto the same line. Okay. However, they are not in the same line. And if you now if you follow this particular feature, then you will also convert this thing into the your other isomer, your other diastereomer. So I am converting this again. Again I am explaining to you in the next page. This was my picture. Please remember, this was my last picture. Here you see hydrogen, OH and CH3, and then I am having my this part where my CH3 group is here, and then my pH is here, and then again hydrogen. So I am drawing my front carbon here. So my front carbon actually is with this color, so I am writing in that manner. So this is my CH3, this is my H, this is my OH, and this will go down, and then I am having my rear positions. This is my CH3 here, and this is my hydrogen, and this is my pH. This is your, see, this was your Newman projection, this is your Sohor's projection. Okay, this CH3, this is CH3, this is the hydrogen, this is the hydrogen, and this is the pH, this is the pH. And don't forget, you are viewing your molecule from this particular direction. Okay, now I will convert it into the Fisher projection by the rotation of the 180 degree. So when I do the 180 degree rotation, so what I will have here, hydrogen, CH3, and this is the OH, and then you see after 180 degree rotation my CH3 will come here and my pH will come here and my hydrogen will come here. Okay, say this will come down, this will go there, this will come here, and then again what I can do, I can number it. This is 1, this is 2, this is 3, this is 4. So right, first one is the CH3, so I am writing CH3 here. Fourth one is the CH3, so I am writing CH3 here. And my carbon number 2, which is this one, having OH on the right hand side, so I am writing OH here and H here, and here you can see H on the left hand side, so I am writing H here and the pH here. So I am writing this in that particular manner. Okay, so if I go back, you see these two hydrogens basically are on the opposite side, but here these two hydrogens are on the same side. If you check the configuration of this one, please remember, if you check the configuration of this one, so you see this is pH, H and CH3, and if you go back, pH, H, CH3, that means this is your R. So again you see this is your R configuration, and now you can see here this OH is on the right hand side and H on the left hand side, but earlier one your OH on the left hand side and the H was on the right side, so this was S, but here you see the positions of these two have changed. That means it must be S in nature. It must be sorry, not S, R in nature. Sorry, it must be R in nature. So these this isomer is having R and R configuration. The earlier one is having the R and S configuration, and by definition diastereomers are those isomers which have the different configuration at least on the one carbon atom. So this one and that one, right? These two are the diastereomers. Okay, that this is the concept of the diastereoselectivity, right? And this would be the your minor one, say 30%, around 30% it will form. Why 30%? Because this particular isomer is forming by the approach which is against the Cram'S rule, because Cram'S said that your hydride or your R will actually approach to the nucleophilic carbon from the side of the smaller group, but here it is attaching from the side of the medium group, which will increase the repulsion. So this product would be the minor product, right? So that's why it is only of 30%. Okay, so this actually I have explained with the help of the one enantiomer only, or you can take the you can take the another where is the product, right? This one, you can take the another enantiomer to understand or to know the little more detail about this. So this is your model. Okay, now moving to the next one. Now the Cram'S chelate model. So when we will follow the Cram'S chelate model, again it is very, very important. So for the to follow the Cram'S chelate model, it is very, very important that your alpha carbon must have the groups. See, I am writing here alpha carbon of carbonyl compound. Carbonyl compound if has like your OMe group, right? OMe I am writing here, let's say OH group or say NH2 group, right? So due to the presence of this oxygen here and nitrogen here, this can also coordinate this reagent actually, this group actually which is present in the substrate, it can also coordinate with the your reagent. That means double coordination will occur, and when the double coordination will occur, a ring will form, and you know the ring in the chemistry is known as the keel or the chelate. So that's why the chelate model will be followed in that case. So how we can see this thing? So first of all, you should remember this particular point. If your chiral center, right? If your chiral center in the ketonic compound contains alpha group, that means group present at the alpha position, such as your OMe, OH or NH2, and these are capable of coordinating with the reagents. So the stereochemistry of the product would be predicted by the Cram'S chelate model only. That means the cyclic model. So how we can see, I am giving you the only general example for this one, only general example, okay? And if you want, then you can draw the real example as well. Say for example, I am having my oxygen here. I am straightforward drawing my Newman projection, right? This is the ketonic part, and now I am using the different color for the rear carbon, and this actually is having the OMe group, okay? And say this is your RS, that means smaller group, and this is your RL, the larger group. So if you want, then I can draw this for you. Say this is your OMe, right? And along with this, oh sorry, not OMe, I am very sorry. This is having your R. Okay, this is carbon double bond oxygen, and this R which is present here. Okay, and then you see this is having the group. So this is OMe, and this is RL, and this is say your RS. So this is your principal functional group, ketonic, and this is your alpha carbon, and that alpha carbon is having the OMe group. Okay, so now this oxygen can also coordinate with the attacking reagent. So for example, here I am taking this organometallic compound Mr dash. So what will happen in that case? This oxygen can coordinate with the metal, and this can also coordinate with the metal. So you can see here a ring is forming here. Sorry. Let me reshift it. No, just like that. Sorry. Now, one ring is forming here. See, this is where the chelate or the ring which is forming here. Just like that. This is the 5-membered ring. How 5-membered ring? I can give the numbers as well. Say this is my electrophilic carbon 1, this is my oxygen 2, my metal 3, and my oxygen of the AME 4, and my rear carbon, which is this one, right? Rear carbon, which is this one, right? So it is forming a 5-membered ring. In that case, basically you can follow the chelate model. So in the chelate model, what will happen? You see, this is my pathway A, and of course we will also do the protic workup here. We'll also do the protic workup. So in the pathway A, my R actually, this R will join this particular thing from the side of the smaller group. Okay, that means this will have R dash because it is coming from here. So this is R dash. This will become OH and it will be pushed here. So I am writing OH here, and in the bottom I am having my R. So this is R, which is this one, OH, which is on this particular side, and this R is coming here. So it is present on this particular side, and the rear carbon you are having the different types of the groups, right? So OMe, and then you are having your RS, and then you are having the RL. Okay, so you see here, this is your RS, which is this one, this is OMe, which is this one, RL. So this is one of the isomer because it is coming from the direction where the smaller group is situated, right? So definitely it would be the major one. Okay, and if it is coming from that particular direction, you can also form the minor one. So whenever you have these types of the groups present on the alpha carbon, then you need to understand this chelate model. However, the stereochemistry would be the same as it was predicted by the Cram'S open chain model. Stereochemistry would be the same whether you use the Cram'S open chain model or your chelate model. It is something very important. Please remember. And again, if you go through the Nasri Guru book, it is clearly written over there. In this particular model, the metallic part of the reagent, right, coordinate to form the 5-membered ring. If the chelating group, right, this is the chelating group on the alpha carbon, if it is the medium one, right, see, this is a large group, this is a smaller group, then definitely this OMe is the medium group, right? So whenever the chelating group is the medium one, and it is generally happens that the chelating group is the medium one. In the most of the cases, the chelating group is the medium one, right? Then the cyclic model predicts the same stereochemistry as predicted by the open chain model. But it is very important to remember that this stereoselectivity, diastereoselectivity would be very high in case of the chelate model when compared to the open chain model, right? But if this group is not the medium one or large or the RS one, then this model will predict the stereochemistry opposite to that of the Cram'S open chain model. It is again very important to note that, right? And lastly, in this particular concept, you see Cram'S dipolar model. So what is the meaning of the Cram'S dipolar model? So in the, see, for example, for the Cram'S dipolar model, I am giving you this particular compound. Say this is your ketonic group, right? Okay, and this is a rear carbon, and rear carbon is having your larger group and say your smaller group, and then you are having the halogen here. X is the halogen, electronegative group, not exactly the halogen, but it is the electronegative group. Generally we can say it is halogen. So what will happen when the halogen is there? So this bond, actually, this is the polar bond, this is also the polar bond now. So there occurs the repulsion between them. So in order to minimize this particular repulsion, this X actually is goes anti-parallel to this double bond oxygen. So the configuration would become just like that. You see, if I draw the Newman projection for this one, this is my oxygen, okay, and this is my R, the front one, right? This is my this system, this is R, okay, and this is my rear carbon, and you see this is your X, so this will come here, X, and then you see my RS will come here and my RL will go there. So it is something very important, because this bond and this bond, they are polar in nature. So if a strong electronegative group like halogen atom is present at the alpha carbon, which is present here, the dipoles of the carbonyl bond and the CX bond opposes each other, and it is better, this CX bond is better placed just anti-parallel to this carbonyl group in order to minimize the repulsion. And of course, when the repulsion minimizes, the electrophilic nature of this carbonyl carbon also increases, and the rate of the reaction will also increase, right? So when this happens actually, and you have your say organometallic compound Mr dash, so this will coordinate to this one, just like that, okay, and then from the side of the smaller group, it will attach to this one, and then you are having your product. Since this R is coming from here, that means this would be your with the front carbon, this will form your R dash. So I am writing R dash here. Of course, protic workup will also be there. Okay, and this will become OH, so this will go in that particular direction. So this is your OH, right? And you see when this happens, and this R basically, this R dash is R dash was here actually, and this R will be placed onto this particular direction, and then you have the rear carbon, that means the back carbon, and your back carbon will have halogen here and RS here and RL here. Again, this is one of the isomer, but if you want, then you can draw the minor one also. It will come here, so your R dash will come here and OH will come here. I can draw in the second pathway as well. So in the second pathway you will find this thing. This is where say R dash, this is where OH, this is where R, and then the rear carbon. Okay, under the rear carbon you are having large group here, and then a smaller group here, and then X here. So again, these two are diastereomers. You can take the real examples as well. Okay, so this is all about your Cram'S rule. However, this Cram'S rule is outdated now, but still we use this Cram'S rule in the various examples, but it has its own limitations, right? Because it is only the qualitative method. Please remember, it is only the qualitative method. Only diastereoselectivity can be predicted, but amount we cannot predict with this one. Also, the diastereoselectivity predicted by this is not very accurate in many cases. So we need another important models, and that another important model is your Falcon and model, and I will discuss that Falcon and model in my next class. I hope you understood the things. If you like the lecture and understood the things, please give thumbs up to the lecture, and please subscribe Tetrahedron Chemistry classes, and I'll meet you in my next lecture. Thank you very much.